Welcome back to ECE 442-542. What I would like to do in this presentation is to derive or develop the equations that allow us to go from a continuous time state space representation into a discrete time state space representation using a zero order hold equivalent. This is a discrete equivalent approach among many, but the zero order hold equivalent makes sense when we are trying to apply it to a system that's represented by the block diagram that's shown right here. We have an analog plant or a plant that's evolving in continuous time. We may want to control that with a discrete time controller, and because of that, we now would like to look at the plant or the system in terms of a discrete time representation. Meaning, we now have the commands coming in from the controller going through a zero order hold, and those will then be applied to our analog system. Our continuous time system is described in the conventional state space representation as x dot equal ax plus bu, y is equal to cx. And remember, x is this tall, thin vector that could be 10 rows tall, and obviously if it's a vector, it only has the one column. Our goal is to take that continuous time system, x dot equal ax plus bu, into a discrete time representation maintaining the state vector x and the output vector y and the input vector u. It's just now that those vectors are evolving in a sampled sense or at discrete instances of time determined by the sampling period capital T. And sometimes we may simply suppress that capital T in all of these arguments, and we may just say x at n plus 1 equal phi x of n plus gamma u of n. We would then either have to be told what the sample period was, capital T, if we wanted to figure out what the true time was, or we may just assume that it doesn't really matter in the development that we're looking at. There's two main concepts that are going to hold or be used during this development from the continuous time state space to the discrete time state space. One of those concepts is that we are only interested in evolving this continuous time system over one sample period, and then we'll do it again, then we'll do it again. So we really only need to know how do we solve this continuous time system over a time interval that is equal to a sample period in duration, capital T. The second concept that we will be using in this derivation is that over each of these one sample period intervals, we're going to hold the input constant, and that's really what the block diagram is saying. We inject an input signal, we hold it fixed or constant during that one sample period interval. That drives the continuous time plant, and then we just repeat that process at the next sample period. We get a new input, we hold that input for one sample period of time, and we move on. Those are then the two main concepts that we will be using in this derivation. Now that we have this goal in mind, that we want to convert this continuous time system by means of a zero order hold equivalent technique, what we will need, or what we will do, is actually look at the solution to this continuous time system, and that solution is actually given by the following expression. The expression relates an initial time vector, x at t naught, that evolves over some interval of time, little t, from t naught, and that evolution from that vector x of t naught is propagated through this matrix exponential e to the a times this scalar interval of time, little t minus little t naught. And then we have to also add in the influence of the input u of t that is a convolution with that particular system's response characteristics, which again is determined by that matrix exponential e to the a, let's say gamma or sigma. And in the convolution, we have this flip and slide notion. So one of those functions of time needs to be flipped in time and slid with respect to t, and that's really what that solution is telling us. We have one piece of the solution due to where we started at that instant of time t0, the state vector where it began, and one piece of the resulting state vector due to the input over that t naught to t interval of time. If you're interested in where that solution comes from or how to justify that solution x of t to that continuous time state space system representation, you can check out the link that's provided on the course website, on the D2L site, and that is described in Theorem 2.6 in Professor Andrew D. Lewis's notes, A Mathematical Approach to Classical Control. If you're interested then in where that comes from, you need to see that reference, or how you can justify that x of t indeed is a solution to that continuous time system. Once you have x of t, it's just a very straightforward process to obtain the output y of t, which is just x of t pre-multiplied by this output matrix, capital C. If you want y, the output, then you simply have to multiply or linearly combine the states x of t by this output matrix C. Let's now move forward with deriving the discrete time version in a state space setting based on this original continuous time state space representation. Here's now the derivation of the zero order hold equivalent. What I said before is we have these two concepts that are going to be in effect. One is that we are interested in evolving from one instant of time, let's say the nth sample period, so we'll let the beginning time t naught be little n capital T, and let's let the next time that we're interested in be one sample period later, which just means that we are now looking at little t being equal to the quantity little n plus 1 times the sample period capital T. With that definition, we can now see that t minus t sub 0 actually simplifies to become exactly what we said it was going to be, or that we were interested in. That time interval, t minus little t naught, is actually equal to the sample period capital T. The other concept that we said we were going to be living with was the fact that our input over any particular sample period interval, capital T, let's say that we're saying that that's now u as a function of gamma. Gamma is our independent variable. We are going to set that equal to whatever it is at the beginning instant of that sample period, and we're calling that in this case t sub 0. Or if we've now called t sub 0 little n capital T, we are now saying u of gamma for all gamma between t naught and t, we are going to let that input u be a constant. Which means that between the nth sample period and the n plus 1 sample period, we are going to be holding our input constant at a value equal to the input at the beginning of that sample period interval. And we'll just call that u of t naught, or u of little n capital T. If we now apply those definitions for little t naught, and u of tau in this formula for the solution of this continuous time state space representation, we now end up with the following expression. We can now say that x at time t, little t, which is now defined to be the product of little n plus 1 times capital T, that's equal to e to the a, little t minus little t naught, which we just showed was equal to one sample period, capital T, times x of t naught, which is just x of little n, capital T. That's the first piece that makes up our state vector at the next time instant. Then we had the part due to the input, and that was this integral from t naught, which is, again, little n capital T, up to t, which is little n plus 1, that quantity times capital T, e to the a, and now we have t, which is n plus 1 capital T, that was a little t, equals the quantity little n plus 1 times capital T minus tau, b, that's our input matrix in the continuous time system. And now remember, we were going to assume our input was constant between little nt and the quantity little n plus 1 times capital T, which means that we can actually factor that input outside the integral because it's not a function of the variable of integration. We now have this particular piece all multiplying the input u at the beginning instant of our sample period. Well, the first piece of that's not very complicated. That's just a matrix exponential evaluated at the sample period, capital T. Let's examine this square bracketed piece, which is really the more interesting piece. It's this convolution integral in terms of matrix exponentials, but we can actually, with some observation, simplify that or make that look a little bit better. In order to do that, let's go ahead and define a new variable mu, and let's let that be little n capital T plus t minus tau, or really just the argument inside that matrix exponential. That says then, if that's what mu is, then d mu, since capital T and little n are constant, then the differential of mu is actually minus the differential of tau. And at the lower limit of integration, which tau was equal to little n capital T, we can now find that mu, if mu is now our variable of integration, mu now becomes nt plus t minus nt, or that becomes capital T. And if we look at the upper limit of integration, when tau is now equal to the quantity little n plus 1 times capital T, mu now at the upper limit of integration becomes nt plus t minus n plus 1t, which actually evaluates to 0. If we now use those new variables, mu, into the expression and allow our limits to be now taken from the lower limit when tau was equal to little n capital T, that's corresponds to mu equal to t, and the upper limit is now 0, e to the a, we replaced all of that mess that was multiplying a with just this new variable mu, b, and now we have this minus d mu. But if we remember our integral properties, if we negate the integral, that's like flipping the upper and lower limit of integration. We have a negative sign. If we cancel that by multiplying by minus 1, we now have converted or can rewrite that integral to be an integral from mu equals 0 up to mu equal capital T, e to the a mu b d mu. And if we want, a lot of times it's easier to do this multiplication before you integrate, but we don't have to have that input matrix inside the integral per se, and so we could say that now we just have to integrate this matrix exponential e to the a mu. But typically e to the a mu is a large square matrix. B may not be quite as big, and so if you multiply e to the a mu by b, you won't have to integrate as many pieces. With that simplification, just by a change of variables of integration, we now have x at time little n plus 1 capital T equaling e to the a t x of little n t plus the integral from 0 to capital T e to the a mu d mu b, and now we have that term in square brackets earlier times or scaled by or shaping the direction in which the input u is propagated into or through the state vector. And we can actually simplify this if we want to. We can now call that a matrix. We can say that's just a matrix phi, and we can call this another matrix. We can simply perform the integration and evaluate at the upper and lower limit and call that square bracketed expression a new matrix gamma, which now allows us to write down our discrete time state space representation for the zero order hold equivalent of a continuous time system as x at time n little n plus 1 capital T phi x of nt plus gamma u of nt. Those are our dynamics of our system, where phi is equal to e to the a t, and gamma is equal to this integral from 0 to t e to the a mu d mu b. And we also can have our output equation for that state space representation. It's simply a constant relationship relating the state vector x to the output y by means of this output matrix C, or y of little n capital T is equal to the output matrix C times x little n capital T. This is now our output equation. The combination of those two now provide us with our state space representation that we're after. Now, it's probably best to actually compute these phi and gamma matrices numerically. We may go through an example later by hand to show you why it may or may not be a good idea to do it by hand, but let's now look at how we can manipulate that matrix exponential to actually produce a numerically nice way to compute phi and gamma for these discrete time state space representation. So here are some manipulations. with the matrix exponential. First, let's just try to get a feel for what this matrix exponential is. If you remember the scalar formula for an exponent, e to the x, that's now this series expansion, 1 plus x squared over 2 factorial plus x cubed over 3 factorial, and that's an infinite series expansion. The matrix version is consistent with that structure. Now if we want to compute a matrix exponential e to the matrix A, instead of 1, we now have a square identity matrix I, which is the same dimension as our matrix capital A. Then we have plus A plus, and now we have a squared over 2 factorial. Remember, 2 is just a scalar, so it can be in a denominator. Then we have a cubed over 3 factorial, etc. That's not quite what we have. We actually have that A matrix being scaled by the sampling period capital T, but that is a sort of a trivial modification to that matrix exponential expression. We now have phi is equal to e to the A capital T, which now says that we have I plus AT plus a squared t squared over 2 factorial plus a cubed t cubed over 3 factorial, etc. Now, that's maybe not the best way to compute that matrix exponential, is to start squaring and cubing and raising a to the fourth. That's usually not very nice numerically, but if we make some observations, we can actually improve the numerical properties of that process of computing phi. If we want to create this phi matrix, then we may want to write it as I plus A times T times a new matrix psi, where this psi matrix is actually another infinite expansion, but it's now I plus AT over 2 factorial plus A squared t squared over 3 factorial, etc. Or that, if we wrote it in a more condensed form by using this summation symbol, that's this sum from 0 to infinity of a to the n t to the n over little n plus 1 factorial. Again, calculating psi, that matrix psi, by forming a and then a squared and a cubed, raising a to a higher and higher power is not very nice numerically, so we probably should be doing it better or in a more satisfying numerical way. So it's numerically best to approximate or to evaluate that psi numerically with this nested product, where this nested product is not an infinitely long product. It's now truncated to some finite integer, capital N, but typically we don't have to go very high with capital N for this psi to be a nice formula. So psi now we can approximate by the identity matrix A plus AT over 2, and now we have this nested set of expressions where AT just continues to be divided by the next integer in that expression. And we just keep going until we decide that maybe we've computed enough, and we now have capital N minus 1 times I plus AT over N, and we then are finished. To compute that, you would probably then say, okay, what's my capital N? Let me pick that. Let me compute AT over capital N, add the identity. Now you have a new expression. Multiply that by AT over a new number, which is N minus 1, and you sort of work your way from the innermost term to the outermost AT over 2, and then add the identity to that. And once you've done that, once you have psi, now you can compute the system matrix for the discrete time representation, which is phi, by scaling that psi by A, the system matrix of your continuous time system, times the sample period t, capital T, plus the identity matrix. So there's our phi, which allows us to compute that matrix in our discrete time representation. Now it would be nice to figure out, can we numerically compute this gamma without having to maybe perform this integral? And we can also do that numerically. And that takes a little bit more manipulation to show where that might be coming from. So let's manipulate the input matrix. Our input matrix, gamma, is equal to this integral from 0 to t, e to the a mu d mu times b. But remember what that matrix exponential looks like. It's just this series expansion of I plus a mu plus a squared mu squared over 2 factorial plus a cubed mu cubed over 3 factorial, etc., d mu times b. And now we can actually integrate that term by term, and it may not look so intimidating versus trying to integrate that matrix exponential. Now if we integrate the identity, d mu, that just gives us I times mu. We integrate a mu. Again, a is a constant. We're just integrating with respect to this independent variable mu. We now have a times mu squared over 2 factorial, or 2, plus a squared mu cubed over 3 factorial. Just one more time, we have a cubed mu to the 4th over 4 factorial. All of that now needs to be evaluated at the lower and upper limit before we multiply on the right by the input matrix B. Mu scales all of those, so the lower limit of integration is really not going to give us any term in that result, and we will end up then with I times t plus a t squared over 2 factorial plus a squared t cubed over 3 factorial, a cubed t to the 4th over 4 factorial, again, all scaling by b. But if we look at that, we can see that that's now this sum from of a to the n, t to the n plus 1 over n plus 1 factorial, n equals 0 to infinity, all times b, and that's looking a lot like this psi. It's just that some of our indices are a little bit off, and in particular the exponent on our sample period, capital T, but that just represents one more term, t to the n times t. T is not a function of little n, and because of that we can actually factor one of those t's outside the square bracket. we now have a to the n, t to the n over n plus 1 factorial, n equals 0 to infinity. I've now accounted for that n plus 1 by factoring it into a t to the n times t, all times b, and now that is what we wanted. This is now that psi times tb. And that's now what we need to numerically compute the system matrix in our discrete time zero-order hold state space representation. That's the identity matrix I plus a t psi, and our gamma matrix, the input matrix in the discrete time system, is psi t b, with psi equal to this finite sum, or we're approximating it by that, I plus at over 2 times I plus at over 3, etc. And we just keep going down to I plus at over n. We decide what capital N needs to be to give us the accuracy that we need, and then compute psi, and we can then quickly form our system matrix phi in the discrete time system representation, and our input matrix gamma. And that completes this presentation of the zero-order hold equivalent of a state space representation.